Hello, calculus students. And today we're going to be moving on with derivatives of exponential functions. So as we already saw, if you are given an exponential function e to the x, then its derivative is also e to the x. There and there. Derivative, original. So the only thing we're going to take a look at, and I'm going to go through this very quickly, is the skills from other concepts of derivatives are pretty much the same thing. Chain rule. So e to the power of a little bit more complex expression in the exponent. That's what the g at x refers to as. So it's not going to be just e to the power of x. It'll be e to the power of something a little bit more complex. Chain rule tells us we need to take the derivative of the exponent. Technically, we are still taking the derivative up in the original one because the derivative of x is 1. But it's just not shown because it's quicker to do without. So I'm going to quickly go through some examples. Differentiation. I do mean very quickly. Actually, I'm going to do all three of these at the same time. So as you can see, it's just a little play on some of the derivative concepts you've been looking at before. So the exponent here is 3 to the x, so the chain rule is required to take the derivative of the exponent to get this final expression here in a. In b, once again, your coefficient is left alone. It's an exponential function, so the derivative is exactly the same, but then taking the derivative of the exponent. Once again, exponential function, but the exponent is very complex, relatively speaking. So the derivative is exactly the same function, but chain rule tells us to take the derivative of the exponent in this case. So not really that surprising. Things get a little bit messy in terms of product rule, just in terms of how to work things out. So we'll go through this one a little bit slowly. Your independent variable x appears in two separate functions, the linear one here and the exponential here. That's why you need your product rule. So you can, as we talked about before, identify your f and g. There's your little memory tool. And then it's f prime g plus f g prime. So the derivative of an exponential is an exponential. Keep everything exactly the same. Chain rule, the derivative of the exponent is for the exponential. So what's required to match your answers at the back of the book, which I'll be expecting as well on any summative evaluations, common factoring. So there's a 3 common factor, reminder that plus and minus signs are separators. So there's a 3 on both sides, there's a common factor there, but there's also an e to the power of negative 2x minus 1 as a common factor. So since you have removed both factors here, technically there's a factor of 1 still hiding here. That's where this is coming from. This has been removed as a common factor, that's been removed, that's left over, and so is that little x. Sorry, underlined too much here. All right. So there's your final result, and those are the types of answers you'll see in the back of your textbook. All right, quotient rule. Now again, you can, this is an alternative if you want to use product rule. Again, not required to use quotient rule, but you know how much I like it. Very convenient to use the quotient rule, especially in this circumstance. So you have your n prime d minus n d prime. Okay, so just keeping in mind the denominator is a complex power. So you have power rule involved. So the exponent comes down as a coefficient, keep the base the same, decrease by 1, chain rule for that derivative there. And then as we've talked about before, it's common factoring techniques that are required. And we have similar factors here that can be reduced through division to get your final result. Okay, so I did say I was going to go through this rather quickly because a lot of these concepts were covered before. A little bit more slowly, but just to highlight on the main thing. So this is all available for you on the Google Drive, so you can read it all yourself. But one of the highlighted things was this is how we first took a look at the derivative of an exponential, where we discovered that that limit gave us a 1 value. Now, technically, the value 1 can also be rewritten as the natural logarithm of e. We've seen that before when we looked at logarithms. So why is that convenient? Well, now the derivative of, here's your original function, assuming, now this is assuming the base for the exponential function is e. So your derivative would be e to the x, as you're familiar with, but now we're going to add in this natural logarithm e. All right, so that allows us to come up with a new rule for defining derivatives of exponentials where the base is not e, it's anything but e. So the derivative of an exponential that has a base that is not e is here. So once again, you keep the exponential the same, but what you need to do, this is not a chain rule, this is part of the derivative of the exponential. So now you need to include the natural logarithm of a, which is going to be a constant, okay? Keep in mind a is going to be a constant for some of the examples you're going to see, and you'll see them down below here. And that's just a simplified version with the coefficient in front of the variable portion. Okay. Now, things can get a little bit more complex if you have an exponential where the exponent is not just x, but it's more complex. So then you also have to include the chain rule. So your derivative would then be keep the exponential the same, right? So whatever you have, the exponential stays the same. If the base is not e, you need the natural logarithm of that base. But if the exponent is complex, the chain rule tells us you need to take the derivative of that. So the blue portion here is all because of a derivative of an exponential whose base is not e. So here's an example. And maybe I'll get a little hiding thing to help out a bit. Okay, so if this is your function y is equal to 3 to the power of x, the base is not e, your derivative will be the same, 3 to the power of x. Now we know that we have to multiply this by the natural logarithm of the base, which in this case is 3. So this portion is just the derivative of the exponential. You might say, well, why is this 1 here? This is just to emphasize and remind you that always keep an eye on the exponent and use the chain rule. Now here, derivative of x is only going to give us a 1, so really not much in terms of the effect of the overall result. Okay, obviously it'll get a little bit more complex, so you'll notice each one of these expressions, the base of your exponential is not e. Here you have a constant multiplied by an exponential, right? So taking a look at the derivatives for these ones. So the derivative of 4 to the power of 2x is 4 to the power of 2x. Since the base is not e, we need to multiply the result by a natural logarithm of 4. But the chain rule tells us to take the derivative of the exponent. And then the rest of it is just simplifying. And usually what you do is you write the constants or coefficients before the actual variable or function part. So that's what's being done here. If you're wondering what's going on between this step and this step, well, this is just laws of logarithms. So taking the 2, writing it as an exponent for the 4, writing it that way. Might be wondering, is that even necessary? Well, if you want to match some of the answers that are going to be probably in the back of your textbook or online, perhaps, yeah, you might want to practice that. All right, so again, you have an exponential, base is not e. Your derivative is going to be exactly the same function multiplied by the natural logarithm of the base. So that's your definition, or by definition, derivative of your exponential. Chain rule tells us to always take the derivative of the exponent, which in this case is 2x. So that is part of the entire derivative. And once again, these are the portions that have the variable in it. The 7 to the power of x squared, the 2x being multiplied, very, very careful with the brackets, and this is the constant that should be written on the left-hand side of the expression. And the last one, you have a constant and then an exponential. So just as any other derivative, keep that constant or coefficient alone. The derivative of the exponential is exactly the same as the exponential. The base is not e, so we need the natural logarithm of e included as a factor. Chain rule, derivative of the exponent. Simplify. Okay, so one more time. So this 8 has no bearing on this function at all other than a constant. Okay, at least in terms of what we're trying to do with the derivative. So is part of the derivative just as a constant. Derivative of an exponential is an exponential. Base is not e, so we need to multiply it by the natural logarithm of e. Chain rule the exponent to ensure we have the proper derivative, and then simplify from there. Okay. Last part, just a simple application of a word problem. Most of this will be the same. You've done growth and decay many, many times if you've gotten to this point in calculus anyways. So here you have a bacteria culture, starts with 2,000 bacteria and has a doubling period of 5 hours. This is a little bit different than what you've seen before. So assume a normal pattern of exponential growth. So you're asked to find a function to determine the number of bacteria after t hours. So what you got to be careful with here, a couple things. Most of you will be comfortable understanding why the 2,000 is here, because that's the initial amount. The 2 is here because the bacteria is doubling. So your growth factor is 2. If it was tripling, then it would be a 3, and so on. Now, since the doubling period is 5 hours, why this here? Well, think of it this way. If it takes 5 hours to double, and you want to talk about a time frame of 10, okay, then that's really going to equate to 2 doubling periods. So you want the exponent to be the 2. The only way that's going to happen using 10 is taking the 10 and dividing it by 5 to get a value of 2. In other words, the bacteria will have doubled twice in that time frame. So hopefully that makes sense. You do the same thing with 15. So if you're referring to 15 hours, that's going to double 3 times. How does that obtained? Well, 15 divided by 3. So in 15 hours divided by 5, you'd get a total of 3 doubling periods. So the bacteria would double 3 times in that amount of time. That's the sneaky part. The rest of this should be easy. Find the estimated bacteria count after 8 hours. No derivatives involved. Plug in your t, get your result. Determine the rate of change. Derivative, that's what that is, at t is equal to 8 hours, or when the population is 6,062. So you have the t value, you just need to take the derivative, and again, you have constant and an exponential. Okay, now, sorry, gotta go back here. So there's your function with the independent variable. So the constant is part of your derivative. There's your exponential is also part of the derivative, but since the base is not e, we need to take the natural logarithm of that base, which is 2 in this case. Chain rule tells us to take the derivative of t over 5, or 1t over 5, which is 1 over 5. After that, we have the t value given to us as 8 hours, so the derivative after 8 hours, plug in the t value, come up with a result. Calculator obviously would come in very handy here, and then put some units, and you're all set. Determine the length of time it would take for the population to reach 10,000 bacteria. So that is the final amount. So there's the setup for the function. Final amount is 10,000. T is 2,000. Now you might be able to play around and get this answer without even working with anything, but we're going to play around and use a calculus technique. So try and isolate for t. First step would be to divide both sides by 2,000. Then any way you really want to isolate the t. So again, just because we've been talking about natural logarithms for a little bit, why not use natural logarithm? It's not really absolutely required. Could use any sort of logarithm. Logarithm base 10 would work. Take the natural logarithm of both sides. That's useful because then the exponent here will become a coefficient. Now that's going to be a lot easier to solve for t in this format. Now if you're looking for an exact answer, it's the natural logarithm of 5 divided by the natural logarithm of 2 times 5. But since it's a word problem, calculators are fine to continue the results, just keeping in mind t is in hours, concluding statement, and you are done as far as this section is concerned. Okay, so moving on to section 5.4 of your book anyways. So again, these rules that you're going to take a look at are not new rules. It's going to look a little bit more intimidating because now you're putting everything together you've done with derivatives for the last few weeks that you've been dealing with it. So again, I'm going to go through this relatively quickly because most of this should be pretty familiar. You have a function that has two exponentials separated by a plus sign. So when you take a derivative, you're going to take the derivative of the first exponential and the second exponential separately with a plus sign in between, and then simplify. So again, derivative of the exponential here is e to the x. You do not need the natural logarithm of e. You could write it in, but that's going to give you a 1 anyhow. Simpler just to worry about taking the derivative of the exponent 3x and to get 3 there using chain rule. Similarly on the other side, and then simplify. So again, you can identify some rough work off to the side if you wish. That would be more for later questions if you needed to work with this in terms of dealing with a different style of questions. So this is just here as a reference for other types of questions. Derivative of e to the x is e to the x. Derivative of 3 to the power of x is 3 to the power of x. Natural logarithm of 3, if required. But that's just for another question, not for part A. Okay, so here what you have to realize is you have a sine function with the independent variable x and an exponential function with the independent x. Guess which rule you need? Right, product rule. So this is a PR question. Derivative of sine is cosine. Keep the angle the same. Don't forget to use chain rule if necessary to take the derivative of the angle. Times the other function, which in this case is just e to the power of 2x. And then f is just your sine x. So again, maybe for some of you, some work off to the side might help. And then the derivative of the exponential is the exponential. Base is e, so you don't need the natural logarithm, but you do need to take the derivative of the exponent because of the chain rule. And then from there, again, factoring techniques are going to come in very important, and then simplify as much as you can. Once again, here you have a function. There's an independent variable. That's a linear, and then you have an exponential e to the power of cos x. A lot more complex with this one. Still need the product rule though. So your first part is derivative of f, and again, if you wish to identify your functions and then do some side work, probably not a bad idea in this case. F prime is -4. G is e to the power of cos x. Now, careful of this one. So the derivative here is exactly the same. You don't need the natural logarithm of e because that's going to give you produce a 1 anyways, but the derivative of cosine multiplied by negative sine x. So all of this is the derivative of g. Put that into your product law, and that's what you wind up getting. From there, it's simplifying, which you do have common factors of -4 and e to the cos x. And that's it. All right. Now, even though things get changed a little bit, you don't have to use f and g if you want. You can use w and g. Why not? We mix things up with the product rule. Once again, you have a function. It's an exponential. There's your independent variable. It's part of the exponent. That's why it's an exponential multiplied by a trig. So you have an exponential. Derivative of the exponential is the exponential multiplied by the natural logarithm of the base. Now notice immediately the natural logarithm was written as a coefficient. Doesn't matter if you write it that way or not, but keep in mind all these three things are multiplied. Where did the cosine come from? Chain rule, derivative of the exponent. G at x is pretty easy. Derivative of cosine is negative sine, keep the same angle, and the derivative of x is 1, so you don't really need to show that. Okay, now all of this is the first part of your derivative of f over your w prime, in this case, the way I've indicated. So f prime is here. and then g. So be careful of the way this one looks. So the first three, derivative right there. The next one is because the original. Then there's your plus sign. Keep the original for the other function. Take the derivative of the function you did not differentiate. So that's your product rule. And then once again, common factoring is required to get through that. Okay, here, determine local extrema. We're in the local extrema for this function over this particular interval, and then do some sketching. So local extrema, again, are your min-max. So for your critical values, like you've done before, you need your first derivative, which is here. As you have done previously to find critical values, what do you need to do with this? Set it equal to 0. So extremely important, you factor. Without factoring, you're going to have a heck of a challenge trying to solve for x, because that's what you need to do. You need to find x. So these are two separate factors, much like any factoring or finding zeros type of question. Each factor could be equal to 0. Now, with this one here, though, well, e to the x has this type of shape to it. So negative e to the x would look like that, because it's been reflected. Will it ever equal 0? No. So you don't have a solution for that particular factor in terms of finding x. Now you might get a little intimidated with this one here. Say, well, how am I going to solve this one? Well, this is a very interesting way of solving it. There's a couple of different ways you can take a look at it. Obviously, technology can help, but without technology, here's a very simplistic way of approaching this. Something you probably never thought of. Put one of each trig functions on either side and then divide by a trig function that's going to produce another trig function. So your options are divide both sides by sine and get cotangent, or divide both sides by cosine and get tangent. Guess which one I chose? Divide both sides by cosine to get a tangent. Now this is a lot more familiar in terms of finding that x value. Notice I got a little triangle up here, and that's why I was hiding, because the tan inverse of positive 1 is going to give us a related acute angle of beta. Remember that sort of trick? Or sort of related acute angle of pi by 4. And this is all based on your trig. So because tangent is negative in the second quadrant and the fourth quadrant, then we need to find those two angles, because there's two of them that are going to work if you remember the intervals between 0 and 2 pi. So one of them would be 3 pi by 4, because beta is pi by 4. Beta is pi by 4 here, so this one would be 2 pi minus beta. This is pi minus beta. So I have not written down the fact that beta is pi, simply because, well, that's something you should have remembered. So those are the two x values. Those are the critical values we need to determine our local extrema. Okay, so all the skills you've looked at before are coming back into the fold. You now have two choices to determine the local extrema. Create an interval chart or use second derivative. So I didn't complete the interval chart. Feel free to do so, but this is how you would do it. Very painful as far as I'm concerned. A lot of calculator work to determine whether the derivative is going to be greater than 0 or less than 0. Oops. So that's something I'll leave that with you if you wish to do that. I prefer the second derivative test myself. Finding the second derivative is not that challenging. We already have the first derivative. It is a little messy, I'll say that, but that is your second derivative. It is a little ugly. And again, that's basically using product rule a couple times. And you might say, well, that seems like a lot of work. Why would I do all that if I can just do a table? You can do whatever you'd like. Totally up to you. I don't personally think there's an advantage to one or the other. I prefer the algebra myself because I'm more confident with dealing with algebra and derivatives rather than playing with a calculator to come up with certain values, but that is your choice. So if you do wish to see the algebraic approach, this is the way to take a look at it. Take the second derivative. Factoring obviously is going to be extremely helpful. And look how nice all of this simplifies to. Very nice couple of factors. How do you use that? Well, when you have your critical numbers, if you recall, all you need to do is plug those critical values into your second derivative and see what you get. And I just did this not by observation necessarily. It really depends on, again, on your skills. All you're trying to prove is if it's greater than 0 or not. So you could use a calculator, plug 3 pi by 4 into this expression. All you need to worry about is a positive or is a negative. In this case, it's positive, which means it's concave up, which means I have a minimum, and I've identified the local extrema. Similarly, its second derivative at the other critical value turns out to be less than 0, so it's concave down, and you get your local max. Okay. And the last thing to take a look at is finding the y values at those critical points, because you were required to sketch. Might have forgotten that at the beginning. So determine the local extrema. We found those points. We didn't find the y values yet, but you were required to do a sketch. So we know where the critical values are. We need to find the y values. So at those two critical points, substitute the critical points into the original function to get the y values. And the x-intercepts are your zeros. So to locate that, just to get a nice sketch, set again, the original function equal to 0. Do some solving. No solution for the first factor here. When is sine equal to 0? That should be fairly familiar. No issues there, at least I hope not. And then you put the sketch together. So the idea here is you've got the zeros plotted, right? You even have some points you can plot here. So you have an x value with 3 pi by 4 and negative 7. So 3 pi by 4 and negative 7. Now look at the scale. So you've got 10, 20, 30, 40, 50. So each square is 20. So it should be right about there. And then the other one is 172 at 7 pi by 4. So 7 pi by 4 is way over here. So 100 and let's verify 172 is going to be way the heck up here. Somewhere way up there. So we've got a point here, point there, and this is supposed to be your minimum. And up here is supposed to be your maximum. Through the power of magic, or just math, there's your graph. Nice, huh? And hopefully you can see most of it. Maybe we'll come up. There we go. That may be too much. That's a bit better. Okay. So you need the y values to get a proper sketch, and that's why we have to go through a couple of extra setup. And that completes that final example, and that completes the discussion for 5.4 differentiation rules and exponential functions.